So what does that all really mean? Well, it means that we're interested in this capital F of x, which we now know that if we derive, gives us our f of x. Now, that is what we used to call our antiderivative. So we're finding a function that when we derive it gives us our original function. So another way that we will now talk about this is the integral. We're going to start with something called an indefinite integral. We'll talk about later about what a definite integral is. And how we write that is we say that the integral, which is this symbol here, of our f of x, and then this dx here sort of acts as like a bracket. So the integral sign in the dx sort of tells you want to integrate everything in between. And that is our f of x function. And because we remember back to our antiderivatives, remember there's always that a c that might be there that when we differentiate it will get lost. So now this function here, when we differentiate it, will give us our lowercase f of x, or the lowercase f of x, when we integrate it, will give us our uppercase f of x. So really what we're doing here when we're trying to integrate is find the function that when we differentiate it gives us the original function. So let's look at some examples. What if I had 3x squared and I want to integrate that? Well, what I'm asking is what function, when I differentiate it, will give me 3x squared? Well, if I'm going to differentiate something that gives me x squared, it's going to have one higher power when I differentiate it. It's going to be x to the 3. If I differentiate x to the 3, I bring the 3 down the front, so it becomes 3x, and then I minus 1 off, it will become 3x squared. So this here is my integral, because I know if I differentiate that, I go back to this. And then I go to a plus a c, because then maybe there was a c that got lost. So what we're sort of trying to do is find that situation where we can find something when we differentiate it will give us the original thing. Now, there's some little rules we can do. So we can do the integral of x to the n. Well, that's going to equal, well, I know when I integrate this, I'm going to have an n plus, it's going to increase my power because when I differentiate it, it has to go back down. And when I differentiate this, it would have an n plus 1 out the front. So in order to cancel that out, because I can't see it here, I need to do divided by n plus 1. And if I wanted to, I could have some constant there like that. And that there is, for polynomials, my sort of key rule. So let's do another little example here. Just leave that in view. Just get this to focus again. Oh, it's not focusing very well. Let's try that again. There we are. So leave that rule there. So when I integrate this, well, I've got x to the 3, so that's going to become x to the 4, and I want to divide by that new power. This one here is going to be keep the 4 there, increase my power, divide by my new power, and a plus a c. And that's all really what I'm doing with these indefinite integrals. Over the next little while, we'll look at looking at particular functions and how they deal with it, and then we'll move back to that area under a curve.